Thank you, Nandini, Nidhi, as well as Rishi. So these three will be now associated with you all for the semester. They are your immediate seniors, and they will basically be now looking at making you all understand what procedures they followed and what procedures they follow. All right. If you'll know that there is an overlap of the power electronics subject between you all and them, right? So the subject that they have is very similar to the subject that you all have of power electronics. So that's where you all can also take the help of these guys when you're doing the particular experiments as well as theoretical work. All right, Nandini, over to you. Thank you all for joining in.
Yes, sir. Hi, guys. I'm Nandini, and I will be helping you guys out with your DLIC practicals this semester. So I'll be sharing my screen, and I hope I'm audible.
Yeah, yeah. Nandini, if you can switch on your camera, nothing like it, so that they
Okay.
know who it's supposed to associate with, that
Yeah,
becomes
sure.
very understand. Yeah.
Sure, sir. Okay. Let me know if there is any issue with my network then. I'm not so sure if it will be able to handle it.
Sure. So what you can do is you can disable off the incoming cameras so that
Yeah.
you don't get the bandwidth sucked out.
Okay. Okay, sir.
All right. Cool.
Yeah. Hi. Hi, guys. Um, okay. To start off with it, I'll just open LTspice. So this is what LTspice looks like. And to start working on it, you will be clicking on File and pressing on New Schematic. This is where you will be placing your entire circuit and running it. So we will be doing the non-inverting amplifier today. And for that, you will first have to choose an op-amp. And since LTspice already has OP07 installed in it, so we will be starting with OP07 for today. Um, so you will be selecting the component tool over here on the toolbar. And once you press component, you will be typing in which component you want to select. So OP07. So as we can see, this is how your amplifiers look like, right? With all the ports. So you'll be selecting it and pressing on OK. So once you have pressed on OK, you can see that the component is with me and I can place it anywhere, right? So I'll be placing it over here. To place it, you just have to click once. Okay, so once I've clicked it, uh, the U1 is the first op-amp that has been placed, and we just need one. So to select another component or carry ahead, you will have to press escape. Okay, so I'll press escape, and the selected tool is now gone, right? And a few, yeah,
Sorry to interrupt. So, any process that you do, just show it twice so that it becomes easy for them to recollect. So, if you're picking and placing,
okay,
if you always show where is the tool locator, it becomes easy for them to grasp. All right.
okay, yeah, sure, sir. Um, all right, so I'll be picking up this component again. So let's just cut this. So for cutting it, you will be selecting the scissor over here, right? And just left click once and it's gone, right? Now press escape and let's go on the component tool again. So once you left click on component, you can search for the component that you will be opting for. So OP07, right? And left click on OP07 once. And once that's selected, press OK. So now that we have the op-amp with us, you can place it by left clicking once on your schematic. So I've pressed once. And now to go ahead with placing of another component, you will press escape to just get rid of this op-amp now, right? So escape just once. Now there are a few components that we use more often than the others, right? So like a resistor or ground or just the wires, right? So you can see that these components are here and you can just press once, just left click once on it to just take it, right? And to rotate it, since we want to place the resistor horizontally, you will press Control R, right? Control R to rotate it. And to rotate it again, you can, press Control R again. So as per your wish, like however you want the resistor to look. So I want it to look this way horizontally. So I'll just left click once to place it. So left click and another resistor over here, right? Since this is a inverting op amp, we will be using two resistors and one VIN and VCC VEE, right? Um, I'm guessing you have been taught already this today. So uh, till here, I hope I'm clear, right? The resistors and the op amp.
Yes.
Okay. So now we will be selecting the voltage. So for voltage, you'll click on component again and you will simply search for voltage, right? So here's the voltage source. This is how it will look like. I'll just press on it once and select OK. So the voltage source is there with me, and this is a inverting amplifier. So the source will be at the inverting end, right? So Vin will be placed over here. And since VCC and VEE is also given to, these nodes over here on top of the op amp and के नीचे. So let's give it, we will be placing the VCC and VEE over here so that the circuit looks clean. Okay. What you can do is you can, probably just rotate the voltage source by clicking Control R, okay, and placing the positive end over here, but that will just make your circuit look really messy. So to make it clear, what we do is that we place components, and I will be placing the the labels of VCC and VEE, and you can simply put the labels on these ends. Okay, so then it will be equivalent to placing the source over here, right? So once I'm done with it, it will be more clear. um so I hope the voltage source selection was okay. Um, right? Do I show it to you guys again, or was the selection of voltage source fine?
Oh, it's okay. We
It's
understood.
fine, we understand.
Okay. Now, as you guys know that we will be needing this voltage source to be, a sine voltage source, right? So you don't want it to be a DC voltage source. So what you will be doing is that you will be right clicking on the circle. So once you right click on it, it gives you the option of, advanced. So if you just place the value over here, okay, DC value may, if you just give it 1, 2 volts or anything like that, then, a constant voltage will flow through it. But what we want is an alternating voltage, right? So you will be selecting the advanced option. So you will be left clicking advanced and you will be selecting the sign option. And once you've selected that, you can see there are options of the DC offset and everything. So the DC offset over here will be 0, right? And the amplitude can be taken as, let's take it as 1 volt peak. Okay, not 1 volt peak to peak, then it will be 0.5, but we have taken 1 volt peak. So, and frequency can be taken as 1 kilohertz for now. Okay, uh, so I've given the values and then you select on OK. So once that's given, you can see that, it can be seen over here. In the bracket, 0 is the offset, 1 is the amplitude that you have given for the voltage that you've given, and the frequency is 1 kilohertz. So, all right. Now let's connect the grounds, right? So the grounds will be placed. So the positive end will be grounded of the op amp. So I can place the ground over here. So the triangle over here is the ground. Okay. Once you hover over it, you can see it says ground, right? So this is how the ground looks like on LTspice. Um, okay. And the negative end of the voltage source will also be grounded. So ground over here. The VCC and VEE will Sorry, I don't. Yeah. The VCC and VEE will also be connected to the ground. So let me just, yeah. So I've placed the ground over here as well, right? I don't think anything is missing. Yeah, I'll just, yeah. Uh, I hope till here everyone is following through. Yeah, can I carry on?
Yeah, yeah, right. Correct.
Yes.
Yeah.
Do you guys have any doubts how to change the voltage source from DC to AC or anything like that?
I think Nandini, as of right now, everything looks good.
Okay,
Guys,
okay, sir.
you all can interrupt in case if you all have to ask anything. Please go ahead and interrupt. Nandini, as of right now, everything looks good.
Okay, okay, sir. So now we will be connecting all the components together. So we will be selecting the wire option over here. Okay. So as you can see, the pointer is given, right? So you will be clicking on those squares as these are the nodes of whatever components are there on the screen. So I just selected the op-amp ka negative N to the resistor R1, and now we are connecting R1 to the voltage source. R2 will be connected over here. Then this will be grounded. The positive terminal will be grounded of the op amp. And um, okay, one more important thing is that, if you just click once, then the wire, it just stays there. But if you want to end the wire over there at that point, like for example over here, right, the wire is still there. You have to press escape. Okay. And then to place the wire again, you'll have to select the wire option again. Okay. It just doesn't come by itself. Then press everywhere you want the wire to just stay. Otherwise, it can be, just messy lines or, okay, sorry, second. Yeah. This is connected. The VCC and VEE can be connected directly to the ground this way. I'll be I'll be actually labeling the ends of these voltage source. Okay. So these aren't supposed to be just left like this. Okay. Any connection isn't supposed to be just hanging like this. You have to place a label, or you have to ground the voltage source. So for placing the label, what you can do is there are two ways to do it. You can right click on the end. So I have right clicked over here and there's an option of label net. Okay, just left click on label net and give the name. So that was VCC, right? So I'll be giving the name VCC and press OK and give that end the VCC. Okay, so this was one way. The other way of doing it is by choosing the label net from here, from the toolbar. Okay, and just give the name VEE. Okay, and place it over here, the negative, and it's supposed to be connected to the negative uh, input, voltage input of the op amp, right? And VCC is supposed to come here. So what you can do is that you can just place these labels for now directly, and you can edit it later to whatever name you want to give it, right? So I've just placed VEE everywhere. Now I want this to be VCC, right? So I will right click it and you can change the label name to VCC. Then this just becomes VCC. You don't have to do anything else now. And why have I placed a label over here and over here? Because you will be taking the inputs for your output, like you will be placing your pins at over here. So this will be your V out, when you will observe the graph, and this will be your V in. Okay, this is where you will be placing the pins for your output graph. Okay, I think all the labels are placed. Do you guys want me to run through the label placing again?
No, that's
No, there's no need actually.
Okay, fine. Now I will be giving the values to the resistors. Okay, so since we have taken an inverting amplifier, the the resistor R2 can be taken as 3K for a gain of suppose 3, right? Since the formula is minus R2 by R1 for inverting. Take care that you have to take into consideration that this is inverting and not non-inverting. For non-inverting, the formula differs, right? So you will have to change the resistor values for getting the same gain, right? So for 3 gain, you will take R2 as 3 and R1 as just 1K. Okay, I think this is it. Oh, right. So VCC, VEE values are also supposed to be given. So you right click on the V that's written, right? So over here for R, I right clicked on R, right? And I changed the value. So over here, you will right click on V and you will give it the value 15. Okay, you can take it as 14 as well. But it's just that your clipping will be done accordingly. Like your saturation levels will differ according to the VCC and VEE that you're giving. So I've given 15 over here. And I think, yeah, I think this is it. Oh, also, this is very important. It's really important for you to save the file while, as soon as you start, you should be saving it. Since, if you just, if your power, yeah, like you accidentally just switch off your, computer, then the practical will be lost. So I'll just save it as your SAP ID and the name, right? So non-inverting. Okay, and it's a .asc file. So save it. And once it's saved, you can see over here the name has changed from draft 1 to the file name that you have given. Okay, so now that it's saved, you can run the simulation. So there are two ways of editing the simulation, how you want to simulate it. So right now, as of now, like if this is the first time I'll be running it, right? So if I just press run, then it will give me the edit simulation command option, right? But once I just place the edits, then if after that I want to simulate it differently, then I'll have to go to simulate and then I'll have to select this option of edit simulation command. Okay, so we have taken the frequency 1 kilohertz, right? So for one cycle, the stop time can be taken as 1 millisecond, right? But I want to look at 4 cycles. So I will be taking the stop time as 4 millisecond, and time to start saving data can be 0. Okay, and this differs according to the waveforms. If you observe some issues in the beginning of the waveform, then to get a clear picture, you can change the time to start saving data from the reading where the constant reading starts. So over here there won't be any issue, so we'll start with 0 and press OK. All right, so the simulation is this is where you will be getting your output waveforms. Okay, I hope that everyone understood how you will be running it. I mean, we haven't found the waveforms, but are there any doubts?
Will there be a resistor connected to the positive terminal and then ground?
I mean,
Uh,
you can do that, but even if there isn't, this will still work.
okay.
Okay, so I'm right, right? Like,
Yeah, yeah, yeah.
okay. So to look at the input waveform, you will just be left clicking on V in. Okay. So if I click it once, you can observe that 1 volt peak waveform can be seen, right? The green wave. Okay. And to have a comparison to observe the gain, you will be left clicking once on V out. So once I do that, the blue waveform is the V out. Okay, so you can observe I'll be just changing. So okay, I'll just show how to change so that there's a clearer picture of the reading of the input wave as well. So you can see when you hover over this these values, you can see there's a scale coming, right? So you will be right clicking over here. Once you right click, you can see that there's an option of changing the topmost value of the graph. So I'll be changing it to 4 volts. Okay, and I'll be changing the tick to 500 millivolts just so that I can get a clear picture of 1 volt. Okay, 1 volt peak, the input value, and press OK. All right, so now we can see. And just so that your output waveforms differ from your friends, you can also change the color of your waveforms. So how to do that is that you just right click on it. Okay. Once you right click on it, you can see the default color option is there, right? For V out. So you can change that. Suppose I'll be choosing red. Okay. So once I change it, the color has been changed. I'll just do that again for VN. So right click once, um, default color, change to dark blue. Okay. And press OK. All right. So, and to get a clearer picture of, what the peak value is, you have to left click on V out. Okay. If you want to check V out, then you have to left click on V out, and there's a table over here, right? So you can see this is the horizontal value of where your cursor is right now, and this is the vertical value, right? So if you want to check where the peak lies, then you can just um, drag this to the peak, right? So we can see that are getting a gain of 3, right? So 1 volt peak has changed to 3 volt peak, right? And there's a phase difference of 180 degrees. So this is clearly an inverting amplifier. Okay. And one very important thing for your submissions is how to add the name and your SAP ID on the circuit. So how you will be doing that is you will be going to the text tool over here. You'll be left clicking once and you'll add it as a comment. Okay, not as spice directive, since that's different. So as comment, you can add your SAP ID and your name, right? So, and just press OK. You can also like change the font size if you want to, and press OK, and I can place it over here. So just left click once. All right. And so sometimes to get a clearer picture of how your waveform really looks, what you can actually do is like this is how you placed it horizontally, right? Like your tiles are horizontally placed. So you can, as per your preference, you can tile your windows, vertically as well. So how you do that is you go to tile windows, you right click once, and you choose tile windows vertically. Okay, press it once, and this is just how I like to take my snips for m- our practical file. All right, so this is your inverting amplifier, practical. This is how you will be doing it. And for different gains, you will be changing the resistor values. And to actually notice the clipping at the saturation level, you will be changing the R2 value, or you can also change the voltage given, right? So I will be showing you guys that. So let
Nandini,
yeah,
if you can just change the color from blue to possibly another color, because that's very light in nature, so it's
yeah,
very
sure.
yeah. If you could change that, perfect. Yeah, looks good. Yeah,
Okay,
perfect.
okay. So I can demonstrate the clipping, right?
Yeah,
At the
yeah,
saturation. Okay. So since we have taken the VCC and VE values as 15, you will be seeing, like, the saturation taking place at values, 1.5 volt lesser than 15. So approximately it should be seen around, you know, 13.5 or 14, around 14. So let's change the R2 value to 10K. Yeah, we can take 10K. And we can change the input voltage from 1 to 2 volt peak, right? Yeah. So the output is supposed to be more than 15, right? But there is some expected clipping that will be seen. So save it, okay, and then run it. V in, and this is 2 volt peak, and V out. So we can observe the clipping taking place, right? So to get a clearer picture of it, um, just right click on V out once. Okay, here's the table where you can look at the reading and just drag it to the peak. Okay, so the positive peak can be seen as 14.018, right? So this is lesser than 15, which is what we were expecting. And the negative is also going to be minus 14.01. So this is how the clipping takes place at the saturation levels. Okay. Are there any doubts?
guys. Anyone any questions? I think Nandini, your explanation is perfect.
Okay, okay, so okay. So now that we are done with the simulation for OP07, you can accordingly do it for, different op amps such as LM741. Okay, so unfortunately LTspice really doesn't have LM741 installed in it already. So what we will be doing right now is installing LM741 from scratch. Okay, so um, if you guys already have LTspice, then you can actually do this with me, since this can get a little confusing to do by yourself. If not, you can just watch the recording again.
Guys,
So
this is the most important part, right? Right. So the inverting, non-inverting amplifier, you can do it, at your own pace. This particular part where you're actually supposed to add components which are not there as a part of LTspice library itself, that's the most important part, right? Yeah, Nandini, go ahead, please.
yeah, so you will be searching for LM741 T-Spice model. Okay, and once you hit enter, the first site itself, it's reliable. Okay, it's of Texas Instruments. It's a known producer of op amps. And once you scroll down,
What are we, can you repeat what are we supposed to search?
okay, yeah, we are supposed to search for LM741 P Spice model. i'll
Thank you.
just I'll put it in chat. Actually, I've copied it.
Oh, Nandini, I just put it.
Okay, okay.
Thank you.
Yeah, so once you go on the first link itself, it's of Texas Instruments. Okay, just scroll down and you can see that the P Spice model is given over here. Okay, the simulation model. So just left click download once, and the zip file will be downloaded in your download file. Okay, so open the file and extract it. So to extract it, you right click once and extract all. Okay, and once it has been extracted, I would really recommend you guys to control C and control V wherever your folder for this practical is. So um, DLIC prac and just push it in there. Okay. Since it will be easier for you to open the model on LTspice then. Okay. So as you can see that the LM741 for you is going to be a mod file. Okay. And to open that, just left right click, open with, and WordPad. Okay, so once you have opened it on WordPad, you can look at how exactly it looks like numerically, how the op-amp looks on the simulator. Okay, and this can also be seen on LTspice. So go on File, click on Open, and okay, it's very important for you to select All Files option over here. Okay, so all files selected, the extracted folder is opened, and I click on LM741. So once I've clicked on it, I select open, and here is the WordPad, uh, you know, the exact same text is over here. Okay, the only thing is that you need to open it here just so that you can create the symbol. Okay, you can only create the symbol on LTspice. So you can see that the everything is green, right? Just this blue part, the sub-circuit part is blue, right? So you have to right click on it. And once you right click, you can see the option of creating the symbol. So left click, and it says that it has 5 ports over here, right? So we know that we need to fix something. And since it was already downloaded for me, it will overwrite on whatever had been fixed, right? So I push yes. And as we can see, this is the op-amp. This is LM741 and it's rectangular in shape. But we prefer the triangular one. So we will be modifying this according to what OP07 looks like, right? We will try to make LM741 look like this. Okay, so I will be closing this. Um, Actually, I'll be closing it entirely. I'll be closing LTspice entirely. Okay, now go to your files. Okay, go to this PC. Okay, in this PC, uh, enter documents. Okay, in documents, you can see the file LTspice given to you, right? So open that, open LTspice in your documents, then open the library. Okay, once library is open, you can see the symbol file, the SYM file, open that. Okay, once the symbol file is open, you can click on auto generated. Okay, so you will just have LM741 in your folder. So right click on it and open it with WordPad. Okay, only with WordPad. So once you've opened this on WordPad, you can look at how it's given over here that this LM741 is actually a rectangle, right? And we want to change that. So we know that OP07 is triangle in shape. So we will go back to symbol. Okay, and in symbol we will be selecting op-amps. Okay, since it's pre-installed, OP07 is pre-installed, and in op-amps we will be opening the OP07 file in WordPad. Okay, so here is OP07. So OP07 is the first one which starts with O. So you can even search and open this using WordPad again. So once you open this using WordPad, you can see that over here, there's no rectangle written, right? So there's line. And the pin format will also be different from, I'll just open it side by side. So yeah, see, so what we will be doing is we will be replacing the rectangle format with the triangular one, and we will be changing the pin attributes as well. So how we will be doing that is we will be copying all the line commands, right? So control C everything that starts with line, and control V over here, select rectangle and hit control V, right? So that rectangle wala function has been replaced by all the line functions. So now that that's done, we will also be changing the pins, right? So select whatever starts with P over here in OP07, select all of it, control C, and just control V over here at LM741. Okay. So just check if everything has been selected, right? And everything has been replaced over here in LM741 as well. And hit save. Okay. And save it. So once it has been saved, we can just close it all. Okay. Open LTspice. So once you open LTspice, you can open a new schematic. You can go on the component tool and you can search for LM741 is over here. Right now it looks like a triangle. Let's hit OK, and so the rectangular form has been changed to the triangular one, right? So now you can just perform the entire non-inverting amplifier practical on LM741, and you can observe how the saturation level differs and how the output waveforms differs according to the frequencies given. So yeah, are there any doubts in how to um, install LM741?
I think possibly when they do this, they should have a better idea. But everyone is clear on the process, what needs to be done. Basically, you can import any particular device that is not there in your LTspice, right? So all you need to do is go to the data sheet. So if I tell you that, okay, you want the SCR characteristics, you basically don't have an SCR, let's say in LTspice, you get an SCR in LTspice, right? So that is how you are basically looking at any particular circuit at all, that you can bring into any component that exists, right, physically, can be brought into model in LTspice.
Yeah. Another one that we had installed was TL081. So you guys can also install it by yourself, try installing it. And if it doesn't happen, then in the next practical, while we are doing the um, another practical, at that point, we can just guide you on how to do this again, just so that you guys are comfortable with it. But here is the TL081 model as well. You download it, you follow the same procedure, and you'll get the triangular version of it. So now that there's some time remaining, do you want me to explain the non-inverting part as well, or should I show them the frequency when deferred?
Start off with the frequency response part, because non-inverting
Okay,
now should be decently equipped to do it on their own.
okay. So I'll just I'll open the practical.
Yeah.
Uh, yeah. So how you can observe the frequency when the frequency input frequency is deferred, you can see that the waveform also, kind of changes when a higher frequency is given, that is. So let's change the frequency from 1 kilohertz to say 25 kilohertz. That should be fine. And let's take the configuration that we were working with, which wasn't clipped, right? So this was 3K, and yeah, this was it. So let's save and run it. Okay, wait, I had to change this as well. So this will change from 4 millisecond to say 0, 1. Yeah, see, save and hit run. Okay, no, sorry, I have to decrease it further. Think 25K, so it should be 0.004, right? Okay, sorry, 1 second.
4 zeros and then 4, I
Yeah,
guess.
yeah. It's just, yeah. So this was the input, and let's check the output waveform. So you can see that, the output waveform isn't really a sine waveform, it's a triangular waveform. So this happens, and you can actually change the start point from 0. You can shift it to, say, suppose um, something like 80, right? And 80 microsecond, and you will be able to see a kind of a uniform triangular wave. But why this happens is that, the frequency level, it cannot be handled, like the input frequency cannot be handled by the op amp. I think Sir will be able to explain the theory behind it more, and I think he did. If any one of you can tell
No, as of
why.
right now, so because we had to finish the particular we had to finish off inverting and non-inverting. So this gain bandwidth product that we had to talk about, that's still remaining for them. But
Okay,
just so that I'll possibly broach this right now. What happens is
okay,
that basically you have a relation between gain and bandwidth, right? And the gain bandwidth product is always supposed to be unity, right? So if you increase the gain, your bandwidth is going to drop. If you increase your bandwidth, your gain is going to drop. All right. So when you are looking at extremely high gain, or you're looking at extremely high frequencies, this particular op amp, all right. So what you can see, Nandini, if you can change possibly the color from blue to possibly any other color. uh, yeah.
yes, sir.
Yeah. So what will happen is that basically, as the particular frequency changes, all right, this entire op amp starts rather to behave as some sort of a low pass and high pass filter. It becomes a combination of these particular aspects. When we move towards that filter theory aspect of how a simple combination of this particular aspect can actually change, all right. As of right now, we've not introduced the element of capacitors, all right. However, even resistors, all right, will change behavior as your frequency will increase, all right. And as it starts increasing, what will always happen is that you will see one. Can you see out over there that initially as you increase the frequency, what is going to happen is this waveform will start shifting in yeah, along the x-axis also. All right. So your sinusoidal wave ke relation mein, as your frequency will keep increasing, your this particular output will also shift in phase. All right. Because the behavior of a component at low frequency is completely different from the behavior of the same component at extremely high frequencies. All right. So when we speak about the gain bandwidth product, or when we speak about integrators and differentiators, we will come to know why this shift happens. Okay. But as of right now, you can see very clearly that as you will increase the frequency, the information in this particular one is lost, as the waveform has changed shape from sinusoidal to now almost a ramp, right? This should never happen, which means that over here you've exceeded the operating frequency of your op amp. All right. So wherever you see that the operating frequency of the op amp has gone from your original signal to something like a ramp waveform, it means that okay, this is the final point beyond which I'm not supposed to take my signal, right? So that defines the bandwidth in which your signal can play. All right, and ideally you would want always this bandwidth to be as much as possible so that you can amplify signals from different frequencies, right? But when we talk about this gain bandwidth product, right, we'll talk about how there needs to be a balance maintained between gain as well as bandwidth. Okay, but as of right now, this is an excellent demonstration of what will happen if you keep increasing the frequency on this. Go ahead, Nandini.
So, is the
Okay.
maximum frequency mentioned in the datasheet to which we can take it of the
uh,
op amp?
I am assuming yes, there should be on the datasheet an operational frequency, if I'm not mistaken. Nandini, so possibly we'll pull this offline. Let me check on the data sheet, but I'm assuming that the operational frequency of the op amp will definitely be mentioned.
Yeah. So I'll show them how the resistance variability, you
Yes,
know, it.
yes.
Okay, okay. So now what we will be looking at is that you can change R1 into a varying resistor. Okay, so how you will be doing that is right click on the 1K value that was given. Okay, and enter the curvy brackets. Be careful about this, that it has to be curvy brackets, and let's give it the name RA. Curly brackets, actually. Curly brackets, I'm so sorry. And once you name it RA, just hit OK. Okay, so now RA is given, right? And as you could see earlier, that when you hit the text, right? When you hit the text on the schematic, there's the option of entering a spice directive, right? So since this will be kind of a command given, it will be how you will be varying the resistor. So it will be a spice directive. So how we will be the starting and the end limit of the resistor, and the step by which the resistor will increase, it will be given in this directive, in this command. So we will be writing that as dot step parameter. So param is the short form given, and the name of the resistor will be given, so it's RA, right? So now the how we did it earlier was, we took the starting value as 1 kilo ohms and the end value as 10 kilo ohms. Okay, and you can take the step parameter as 2k. Yeah, I think 2k should be fine. All right, so save that and place it anywhere. So I'm placing it over here, right? So I I think the voltage, yeah, I had done this on the gain of 10 minus 10. Actually, the gain will differ over here, and the input will be given as 2 volt peak, right? So why will the gain differ? Because R2 is constant, right? But your denominator will be varying. Since this is a variable, like the name of this thing is called parametric sweep. Okay, so let's just run this. Okay, we will be saving it first. Be closing this. And yeah, this remains the same. Okay, right click vertically, input and output. So you can see that, okay, the clipping is also taking place, since we have taken a value where the output voltage will get clipped, and you can see how the output waveforms are different for the different R1 that will be given, right? So um, yeah. So from 1K to 10K in 2K parameters like difference, you can say that there are five waveforms, output waveforms that are given, which are sinusoidal and so yes. So I think if you want to explain the theory behind this, in case that's needed.
Sir, you muted.
Sorry, I'll do that in the next particular practicals tomorrow, because they'll start off at 3 with IBM, so I'll do that tomorrow.
Okay, okay, sir. So are there any doubts in how we did this? Since I like this can be a little complicated. If there are any doubts, please.
So the only thing that I would want you to explain is what is the reason behind doing the parametric sweep, if you can, or I'll pick it up
Okay.
tomorrow.
Yeah, so the reason we did the parametric sweep is just so that so your formula for your gain is minus R2 by R1, right? So when the R2 remains constant, which is 10K over here, and your R1 keeps differing, then your gain will also differ. So your output waveforms will be according to the gain that is being offered by the op amp for that particular resistance that is being given, right? So for 1K, you could say that we are getting the waveform which is uh, of gain, you know, yeah. So of different gains, you can see different outforms. I can't really pick which one is for which, but
Right.
yeah. So if you want to elaborate on why, like further, then okay,
Right. So tomorrow, I think when they start off, I think they have practicals tomorrow, and that's when I'll explain them why parametric sweep is done. That should give them a very clear idea of why they are doing this.
okay, okay. And just to make things easier for you guys, for in sorry, this was the inverting one. So for the non-inverting one, you can just copy this entire circuit, okay, and just open a new schematic. You can just place it over there, and you can, uh, you know, cut this voltage source and place it over here, okay, and that will be your non-inverting amplifier. Yeah, that's it, I think. So this is it, right?
Yeah, perfect.
Okay.
Guys,
Thank you, guys.
any questions? I think she's done a brilliant job. So anyone, any questions from your end that you would want to ask her? Nandini, for me, this was spot on. Whatever needed to be covered, everything's there on the system.
Okay. Thank you so much, sir.
Yeah.
Thank you, guys.
Yeah. Guys, anyone, any questions?
No, so no questions from my side.
Okay, perfect. So what we'll do is, this is how we are going to be doing it. So Nandini has introduced us to LTspice and how we can add modules to it, or add models that are there from the datasheet. We will also be looking at another tool which Rishi will be introducing to us in the next particular week, which is Orcad. All right, or possibly the first 2 or 3 weeks, until and unless you get a hang of LTspice, we will be working with LTspice itself. All right, however, we will always keep moving to discovering as many tools as possible. All right, so there's Altium that you use. So professional designers use Altium. All right, so how do we move from LTspice to Orcad to Altium, where we can then move to how you do industrial level PCB designing. All right, so your skill based course that you'll have will introduce you to a software called as eSIM, if I'm not mistaken. All right, but these are all the tools, as many tools that you can grasp, and once you understand the individuality of each of these tools, then it becomes worth to discriminate that okay, this is the tool that I want to use because of this particular features it has, as against another tool. All right, so as of right now, at the academic level, LTspice works brilliant. All right. When it comes to industrial PCB designs, it is normally Orcad or Altium that lies at the highest level. All right. Nandini, thank you so much. Rishi, thank you so much, and Nidhi, thank you so much for joining in. This was an excellent session, and I think next Wednesday we'll carry forward with this. All right, guys, if you'll have any questions, I've added all three guys to the team itself. All right, so in case of anything, you all can ping them out, and possibly they could help you out with any particular aspects that you're facing problems on. All right. Thank you so much. I think we can close the session then today.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you.
Yeah.
Thank
Thank you, sir.
Thank you.
you.
Thank you, sir.
Thank you, sir.
Thank you, everyone.
Thank you, sir.
Thank you, sir.
Sir, are you still there, me?
Yeah, I'm there. I'm there. Go ahead, please.
Yes, sir. That day, yesterday, when me, Smith, and Anand came over for doubts, I was hoping that maybe I could come to college this week for like practicals. Like, at
Yeah,
least
you can
stand
come.
with them.
Yeah, you can come in tomorrow. Also, I'm there, so shouldn't be a problem.
Okay, okay, sir.
Yeah.
Yeah.
Okay.
Yeah, sir.
All right.
Thank you.
Thank you. Bye. Bye. Bye.